One day, in one of my high school math classes, I was introduced to a sequence that I'm sure every mathematician has pondered at least once. The sequence goes 1, then 1 plus 2, then 1 plus 2 plus 3, and so on. The nth number of the sequence is the sum of the first n natural numbers. The purpose of the lesson was to learn sigma notation, how we can unambiguously express the sequence like this. But the teacher threw in a bonus, a clever proof that this sum is actually equal to n times n plus 1 divided by 2. This really fascinated me, not just because of its elegance and simplicity, but because it extends the domain of the sum. The original sum is discrete, it only makes sense to plug whole numbers into it. For instance, if we tried to plug in 1/2, we wouldn't even know what to do. But the new formula is continuous. It has no problem handling any number you throw at it. Take, for example, the sum of natural numbers that I mentioned at the beginning of the video. That's just a parabola.
Awesome video. 1341 I would just say the sum of natural numbers should be a piecewise parabola because -1 plus -2 plus n equals negative number, not a positive one. I made a terrible video about the sum of natural numbers if you want to check it out.
But -1 plus -2 plus n isn't the correct extension of the summation function to negative numbers. The summation function is given by the sum from k equals 1 to n of k. If you plug in a negative number for n, then this sum is going backwards and different rules apply here. In the same way that the integral of a negative function can be positive if you integrate backwards, swapping the limits of integration, the same can be true of a sum. Summation satisfies the following key property: if you sum from k equals a to b, and then from k equals b plus 1 to c, and add the results, you will get the sum from k equals a to c. Plugging in a equals 0, b equals n, and c equals 0, we see that the sum from k equals 0 to n plus the sum from k equals n plus 1 to 0 should equal the sum from k equals 0 to 0, i.e. the value at 0. Rearranging, the sum from k equals 0 to n equals the value at 0 minus the sum from k equals n plus 1 to 0, or cancelling the common value at 0, we can say that the sum from k equals 0 to n equals minus the sum from k equals n plus 1 to minus 1. Applying this to the sum from k equals 0 to n of k, for example, we get that this equals n plus 1, plus, n plus 2, plus, minus 2, plus, minus 1, equals, n1, plus, n2, plus 2 plus 1 equals nn1 slash 2 equals, nn plus 1 slash 2, a positive number that agrees exactly with the parabola formula.
At JL, thank you for taking the time to respond to me with a well-written proof. But I'm still a little confused. Why are you graphing the sum from 0 to n of k, then the sum of from 1 to n of k? A number line naturally goes from n to n, so should the summation not follow the number line?
There's certainly nothing wrong with defining a function which is a sum from 0 to n when n greater than 0, and a sum from n to 0 when n less than 0, as you do in your original comment. But then it's quite obvious just from this definition that it's a piecewise function. For example, look at the start point and end point of the sum as functions of n. Both of these have a corner at 0. The starting point is n when n less than 0 and 0 when n greater than 0. The end point is 0 when n less than 0 and n when n greater than 0. If you define the interval of summation piecewise, then of course you'll get a piecewise general formula. The more natural function in this case is just take the sum from 0 to n, regardless of whether n is positive or negative. This does mean you have to sum backwards sometimes, but there's no piecewise behavior. The start point, the end point, and the explicit formula area all nicely defined by a single expression.
At JL, the issue here is that the sum from 0 to n of f for negative n is not even a well-defined concept. There are several mutually incompatible conventions for handling this in different contexts, according to their practical and theoretical utility in those contexts, but these are just that, conventions, and it being not unique implies a lack of well-definedness. At the end of the day, we read of the sigma notation as the sum from 0 to n of f, but ultimately, it is just notation and nothing else. The underlying mathematical theory behind the notation is arguably more interesting, but it also reveals why these conventions cannot be substantiated into anything further than just context-limited notations and not actual concepts. What we have is a function f whose domain is a finite set and whose image is also a finite set forming a category, and there exists a linear operator that, when applied to f, outputs the sum of the elements of the image of f. Sigma notation is just a convenient way of denoting this, but it's artificial, and is just that, notation. The actual mathematics of the operator in question work differently than the notational conventions. In fact, you mentioned that a similar thing happens with the integral of a function, and I am here to tell you that this too is not actually accurate. The whole flipping the bounds of integration is an invention of educational calculus specifically, and is not actually something that you are really allowed to do with the integral when defined rigorously. Intervals have no orientation, and there is no real way to incorporate orientation into the various rigorous definitions of an integral. The notational convention is convenient, but there it does not correspond to any actual mathematical concept. In fact, even Wikipedia is carefully about this, noting that if you have a function defined on u, v, then the antiderivatives are similarly only defined on u, v, or subintervals thereof, with the integral defining those antiderivatives being on u0, x, where x lives on u0, v, and where u0 lives in u, v. This much rigor is important when formally proving the fundamental theorems of calculus. Outside of this, though, we tend to ignore this, because it has no real effect on our computations in most situations. It only matters in the context of proofs, so we are fine with ignoring it.
I absolutely agree that it's just a convention. But the whole point of this video is that in some contexts, there is only one reasonable non-trivial answer, only one useful convention to use besides not defined. the negative first Fibonacci number is either undefined, the recursive formula doesn't apply, or it's 1. Extend the algebraic relations. The sum 1 plus 2 plus 3 plus either diverges, by standard definitions of summation, or it's minus 1/12, by other definitions of summation, or analytic continuation. 2 pi doesn't exist. You can't multiply a number by itself by times, or it does. Extend to rationals by algebraic properties and then to reals by continuity. The polynomial x2 plus 1 either has no roots, working in the real numbers, or it has 2. Take a field extension. The equation n plus 5 equals 3 has no solutions. You can never add 5 apples and end up with 3, or 1, introduce negative numbers. All of these are just conventions, but in each of these cases, if you're going to extend the definition at all, there's only one way that preserves the properties that the original function satisfied. In the same way, using the standard definition of sigma notation, the sum from 0 to minus 5 should be 0, you're summing over all natural numbers greater than or equal to 0 and less than or equal to minus 5, the empty set. The only contexts in which someone would want to write down a sum from 0 to minus 5, rather than the correct minus 5 to 0, would be either a context where they wanted it to equal 0, or a context in which they wanted certain algebraic relations in the bounds of summation to extend, or because they want a nice, e.g. analytic, extended function. Given that the whole point of this video is finding the most natural extension of a sum to non-integer entries, shouldn't we be applying the "it's just a convention" critique at the entire video? At AMR, I guess I should step back a bit and say more clearly that I'm in full agreement with the content of your comment. And my own comments were probably worded too strongly and absolutely, as though the extension with better algebraic properties were somehow God-given and unquestionable. At the end of the day, what I really wanted to communicate is just the fact that Eddie's original claim, that there is a natural extension to the negative numbers and it equals n plus ... plus 1, is about as suspect as, for example, using commutativity and associativity of infinite sums to prove that 1 plus 2 plus 3 plus ... equals negative 1/8, or that 1 equals square root of minus 1 times square root of minus 1 equals 1. There was an assumption he made about how things work in the typical setting that doesn't carry over to the extended setting and can lead to inconsistencies. The way I chose to show this was by exhibiting a different extension that satisfies nicer algebraic properties. But I suppose in a sense I inadvertently fell into the same mistake myself. I really should have just emphasized that he was assuming an extension exists, and that even in the space of possible extensions, his was not necessarily the only obvious choice. That is, instead of saying actually, it's not B, it's A, I should have said, well, what if we did A instead? What makes you think B is any more natural? All that to say, thanks for the comment, and for getting me to rethink how I phrase things.
Elvis made.
Given that the whole point of this video is finding the most natural extension of a sum to non-integer entries, shouldn't we be applying the "it's just a convention" critique at the entire video? No, because what the video is doing is very different than what you are proposing we do. In fact, the answer obtained in the video is incompatible with the answer obtained from your proposal. The video does not suggest that we should sum the reciprocals from 0 to -5. To the contrary, the video implicitly acknowledges that this is nonsense, at least in this context, and it explicitly acknowledges that, in functionally extending the harmonic sequence to a function of real numbers with certain chosen properties it should preserve, we must ignore the sigma notation definition, and instead focus on the defining recursion of the sequence, with the given initial condition h1 equals 1. This is what the video did. The answer is not compatible with actually summing from 0 to -5, because as you explained earlier in your comment, which I shall address later, that sum is 0, not undefined. He is not exploiting notation and applying it to a domain to which it is not applicable. He is essentially doing proper, rigorous functional analysis. But the whole point of this video is that in some contexts, there is only one reasonable non-trivial answer, only one useful convention to use besides not defined. Arguably, what the video is doing has nothing to do with conventions per se, as I explained above. The 1st Fibonacci number is either undefined, the recursive formula doesn't apply, or it's 1. Extend the algebraic relations. I do not believe there is any scenario in which any mathematician has bluntly declared that f-1 is simply undefined. In any case, we may constrain the domain of f so that the domain is n, not z, but this is different than just saying f-1 does not apply. To be clear, for whatever domain is chosen in any particular application, the recursion holds everywhere, in said domain. And domain restriction is an actual function theoretic concept, not merely a matter of notation, although admittedly, in practice, bad notation can result in confusion regarding these restrictions. The sum 1 plus 2 plus 3 plus either diverges, by standard definitions of summation, or it's -1/12, by other definitions of summation, or analytic continuation. Now this is an example in which I would argue this is solely about mathematical notation, and -1/12 being the answer is indeed more about notational convention, semantics, than mathematical concepts. Unsurprisingly, this is the one example that is controversial, where it really does not make sense there is a well-defined answer to the problem, because the notation 1 plus 2 plus 3 plus itself is ambiguous. 2π doesn't exist, you can't multiply a number by itself by times, or it does, extend to rationals by algebraic properties and then to reals by continuity. Again, this is a matter of domain extension, domain restriction. However, I will say that I do legitimately think the notation 2π is problematic for various reasons which are not necessarily related to what we are discussing here. The polynomial x2 plus 1 either has no roots, working in the real numbers, or it has to take a field extension. Well, no. This is not a matter of convention. The polynomial x2 plus 1 that is an element of Rx, is a different polynomial than the polynomial x2 plus 1 that is an element of Cx. We happen to notate them the same because we are lazy, but the distinction is real, they are different mathematical objects. Which of the two is being referred to is dictated by context, but this has less to do with notational conventions being used in the way you propose, and more to do with us being lazy and lacking convenient symbols for denoting these two objects differently. The equation n plus 5 equals 3 has no solutions. You can never add 5 apples and end up with 3, or 1, introduce negative numbers. Again, this is not a matter of using notation in a way that is inapplicable like you are proposing. The integer 5 is a different mathematical than the natural number 5. We typically treat them as the same object, because in practice, the distinction is irrelevant. and we can tell which of the two objects the notation refers to from context without any concerns about ambiguity. But for matters of abstract algebra, which you are appealing to, it definitely matters. It is not a convention that the integer 5 has an additive inverse -5. It is a theorem. The natural number 5, on the other hand, has no additive inverse. Again, this is not a convention or a matter of interpretation. It is a theorem. The only natural number with an additive inverse is the additive identity, 0. On the other hand, every integer has an additive inverse. There is no contradiction here, because we are dealing with different algebraic structures. All of these are just conventions, but if you're going to extend a definition at all, there's only one way that preserves the properties that the original function satisfied. But this is not true. It all depends on which properties you want it to preserve, and it actually is impossible for every property to be preserved. So there is some low-level degree of arbitrarity present, and important, a definite non-uniqueness to these extensions. This is why one has to specify the kind of extension one is appealing to. Of course, some extensions are definitely closer to being natural than others in some cases, but in other cases, there is no notion natural extension that can be satisfied in the first place. It is not enough to simply extend something and call it natural. One has to demonstrate that it is indeed the natural extension. But there just is no the natural extension in the case of sigma notation. Unlike with the harmonic sequence being extended to the real numbers, there is no mathematical consensus on the matter. In the same way, using the standard definition of sigma notation, the sum from 0 to -5 should be 0, you're summing over all natural numbers greater than or equal to 0 and less than or equal to -5, the empty set. This is not even the standard definition. The standard definition is formulated in terms of tuples, not sets. This is important, because sets are indifferent to repetition. So you cannot have a sum over the elements of a set and have one of those elements repeat in that set. Also, in a non-abelian group, the order of summation matters, so tuples are used. One would say that the sigma notation from 1 to n of f is the sum, in the abstract algebraic sense, of the tuple, f1, f2, fn. In the case that n equals 0, the tuple being summed is the empty tuple, and the sum of the empty tuple is 0. But it makes no real sense to consider n less than 0, because there is no valid notion of what a -1 tuple is. There are a few mutually exclusive conventions for what to do if n less than 0, but none of them are standard by any means. One such convention is to simply call the sum 0 if n less than 0, and this is convenient if, for technical reasons, you need to consider a function defined over all of z, yet somehow need to only care about what happens for n greater than 0 or n equals 0. A convention that is not less common than this is to instead have a linear operator s such that sfn plus 1 equals sfn plus fn plus 1, and sf1 equals f1 for a function f on z. Then sf can be extended to z via the recursion, with sf0 equals 0 being an immediate consequence, and sf-1 equals f0, being that sf-1 plus f0 equals 0 equals sf0 is another immediate consequence. Hence it goes that sfn1 plus fn equals sfn for non-negative n. Yet there are other conventions. None of them dominate over the others in such a way as to be standard, and as pointed out, there is no mathematical consensus. The only contexts in which someone would want to write down a sum from 0 to -5, rather than the correct -5 to 0, would be either a context where they wanted it to equal 0, or a context in which they wanted certain algebraic relations in the bounds of summation to extend, or because they want a nice, e.g. analytic, extended function. Sure. But these are mutually contradicting, and typical methods for achieving these rigorously exist outside of simply abusing the notation, which is why there is no real standard convention. At JL, I guess I should step back a bit and say more clearly that I'm in full agreement with the content of your comment. And my own comments were probably worded too strongly and absolutely, as though the extension with better algebraic properties was somehow God-given and unquestionable. I do not really think your comment was strongly worded. If anything, I think your conversational attitude has been quite reasonable. I can see that there may have been better phrasing, but I think your comment was reasonable nonetheless. At the end of the day, what I really wanted to communicate is just the fact that Eddie's original claim, that there is a natural extension to the negative numbers and it equals n plus ... plus 1, is about as suspect as, for example, using commutativity and associativity of infinite sums to prove that 1 plus 2 plus 3 plus ... equals minus 1/8, or that 1 equals square root of minus 1 times square root of minus 1 equals 1. There was an assumption he made about how things work in the typical setting that doesn't carry over to the extended setting and can lead to inconsistencies. Well, I agree with you. Your conclusion that Eddie's extension is possibly not as sound as he imagines it is in my opinion, correct. What I find to be faulty, though, is the reasoning you used to achieve the conclusion. I thought it would be informative to point out that your line of reasoning was not necessarily any more accurate than Eddie's, although I do think I understand what you were trying to get at. The way I chose to show this was by exhibiting a different extension that satisfies nicer algebraic properties. But I suppose in a sense I inadvertently fell into the same mistake myself. I do believe that calling x middle.x plus 1/2 the extension of the sum is justified. But I would not use sigma notation in the way that you did to argue the position that this extension is the correct one. That being said, I think I understand why you fell into the same mistake, and it is hard not to. Eddie tried using sigma notation in a strange way, and so it is easy to get caught up on why his usage should have been different. But rather than arguing for a different usage and boiling the argument down to what can basically be called semantics, I think it would have been better to point out that, conceptually, the way he is trying to manipulate sigma notation is not valid in most contexts, and that there is a very good reason why n middle.n plus 1/2 should be regarded as the extension instead, one reason that is not dependent on sigma notation. I really should have just emphasized that he was assuming an extension exists, and that even in the space of possible extensions, his was not necessarily the only obvious choice. That is, instead of saying actually, it's not B, it's A. I should have said, well, what if we did A instead? What makes you think B is any more natural? That is fair. All that to say, thanks for the comment, and for getting me to rethink how I phrase things. No problems. We are all in this together.